Slight change of plans. In fact, our next talk is going to be by Eli Goldweber.
Yep, you got it.
Who's going to tell us about testing specifications in Dafny'.
Hopefully this goes better than the other. All right. Well, good afternoon, everyone. My name's Eli. Thanks for the introduction. I'm going to be talking today about the importance of testing specifications and specifically how we did this in Dafny' by building a specification testing framework and applied it to 6 different open source specifications, finding spec bugs across each. This is joint work with my colleagues from the University of Michigan, Weixin, Armin, Vakil, and Manos, Kapritsos. As we know, when trying to verify a system or an implementation, one starts by first capturing the system requirements in the trusted specification, and then a passing proof shows that the system is verified and maintains all the properties defined in the specification. Verification is attractive for these strong guarantees that it can provide. Tools like Dafny' and recent advances in automation has only increased the adoption of verification, but these guarantees are only as good as the trusted spec. If there is a bug in the specification, then that bug could also exist in the protocol or verified implementation and could potentially be hidden by a passing proof. Current techniques to ensure that a specification is correct rely on manual inspection. The insight being that specs are typically small enough and understood well enough to make this task feasible, but even experts have been found to make mistakes. This is an example from a bug in a notional finance verified smart contract. There was a double spending vulnerability that was the result of a bug in the specification. There have also been a few academic studies that have, through mostly manual means, identified specification bugs in different various systems, though these rely mostly on the manual effort. And so in this work, we're trying to improve the reliability that we can give to one specification through the means of testing. The problem, though, of ensuring a correct specification is difficult by its very definition. Specifications are trusted, so they can never be proven correct, so any attempt to ensure a correct spec will always be best effort in some way. So it's kind of a constant battle between the intent and understanding of what you want your system to be specified and what's actually written in your current specification. So we're trying to show that there's a better way that we can increase our reliance on our specs rather than relying on manual effort, and that's through testing. And we've demonstrated this by building a Dafny'-based specification testing framework that helps facilitate spec testing through automation and a manual testing methodology. When a specification is buggy, it may be buggy in different ways. It could be that it's too weak, including some additional buggy behavior that's not intended, or it could be too strong, which excludes some expected behavior. If a specification is too weak, it may include this buggy behavior, and a developer may write an implementation that also contains that same bug. They may even come to a passing proof, falsely giving the illusion that their system is correct, but it's in fact buggy. In the opposite case, if the specification is too strong, it excludes some expected behavior. So a developer writing an implementation and trying to come to a passing proof, their proof would eventually fail, and they may be left with the question of, is my proof failing because I don't have enough invariance of my proof, I'm missing something in the implementation, or in this case, because the spec is wrong. So having confidence that the specification is correct only helps to alleviate this. In the quest to test a specification to make certain that it's neither too weak nor too strong, purely relying on manual inspection is insufficient. And so we've designed IronSpec, which is a spec testing framework that combines the automation of sanity checking and mutation testing with a manual testing methodology. Before talking about IronSpec specifically, I wanted to share an example of a specification to give some insights as to why this problem can be subtle. Consider a specification for sort, which takes an input sequence of integers and returns an output sequence of integers, and the spec is a single post condition that says that the output be ordered in ascending order. At first inspection, this may appear to be a correct spec for sort, but it's in fact incorrect. This is a mistake that many newcomers might make when starting to specify this. It's too weak because there's no constraint that maps the values in the input sequence to the values in the output sequence. We can illustrate this by maybe picking some arbitrary points to see whether or not it's either allowed by the spec and matches our intent for what a correct specification for sort should actually do. So we may pick some arbitrary values. In this case, our input-output pair is both allowed by the spec and matches our understanding of what a correct implementation of sort should allow. But we may quickly find a counterexample where in this case the output sequence is ordered in ascending order, but it shares none of the values that were in the original input. This is because our specification is too weak and includes this additional buggy behavior that we don't want our method to have. To fix this, we would need to add an additional post condition that says the multiset of the input is equal to the multiset of the output. This effectively strengthens our specification, removing that buggy behavior from our original spec. And then we can see that our two specific examples now match our intent for what our correct spec should allow. In the opposite case, if a developer were to accidentally drop the multiset relationship and just say that the input be equal to the output, they've unnecessarily made the specification too strong, which excludes the expected correct behavior that we would want our specification to have. So having automated and methodical ways to approach this problem can be quite helpful, especially as more and more non-experts are writing specifications and trying to prove their systems. We also leverage the notion that specification bugs, like any type of bug, occur because of a disconnect of intent. There's a disconnect between what's intended and what's actually written in the current specification. Note that specifications are often meant to be abstract, so they may include some additional behavior that the system might have, but that might be considered benign. But if there is a bug in the specification, it's due to this disconnect. And so we leveraged this notion when we designed IronSpec to help guide the testing process in trying to focus on and identifying these potential areas of disconnect, hoping to help streamline the testing process. IronSpec itself consists of 3 different testing techniques: an automatic sanity checker, a manual methodology for writing spec-testing proofs. You can kind of think of adapting unit tests to the realm of specifications, and then an automated mutation testing framework. For the rest of the presentation, I'll go through each of these to give some high-level insights as to how this helps achieve testing in the different avenues that these unlock. Starting with the automatic sanity checker, which simply flags common cases of disconnect between the input and output of a verified method and its specification. So in an extreme example, if there's a complete disconnect between the input and output of a method and what's mentioned in the specification, we can provide a very strong hint that that may be an underspecification. So in this case, we have an example of a method bar that returns a value foo of type f, but there are no post conditions constraining the output whatsoever. Now, in most cases, this may not be intended, and so we can flag this with pretty high confidence to direct the developer to say this is missing. In a less straightforward case, there may be only a partial disconnect where part of the output is constrained. So in this case, the output is a data type with multiple fields, and only one of the fields is constrained. So we are still able to flag this, but with less strong of a hint. It may not necessarily be a specification bug. That's kind of up to the developer in the specific context of the system. But the hint is focusing the developer on that specific aspect that may have been missed. As another example, we can revisit our 2-week sort specification from earlier, and we can apply the same reasoning. We can map the output to what is mentioned in the single post condition, and we can see that the output is constrained, and every index in the output is constrained in some way. But we would see there's a complete disconnect because there's no constraint concerning the input whatsoever, which is actually the reason why we were able to see that counterexample from a few slides earlier. Note that these are just hints to the developer. They're not outright indicating a specification bug, and they still will require some manual effort to diagnose or exonerate, say that this is actually intended. But the tooling we actually are providing to help answer these questions takes the form of a spec testing proof. This is a manual methodology for writing tests similar to unit tests, but for specifications specifically. So they're still proofs, but rather than trying to prove the whole system correct, each proof is about a very specific, context-specific question that we wish to ask about our specification, and we can ask different questions by forming our STPs in different ways. As an actual example, we can revisit our sort example from earlier, and we might try to write a correctness STP where we're trying to show that our specification is strong enough to reject some intended invalid output. Where the notion of intent comes defined by the developer themselves, they have to act as the oracle. So like a unit test, the developer would specify context-specific values that they wish to test, in this case as preconditions. And furthermore, because we're testing the strength of the specification, this example is an example of an intended invalid output because the output drops the value that was contained in the input. The proof obligation is the negation of our sort spec, and if our specification is correct, we would hope that we would be able to prove this lemma. But if we run this with our 2-week sort specification, we would find that this lemma fails to verify. But because this is a proof, we're not certain if that's just because we have missing proof annotation in the body of this lemma, or because our specification is actually too weak and we can't actually prove this obligation. So if we become suspicious, we may choose to write a counterexample, where in this case we can structure it pretty much identically, except we're trying to prove the opposite. We ask the question of if our specification is indeed weak enough to prove this case, and with our 2-week sort spec, we would see that this would automatically verify, which is a counterexample to that 2-week spec. So far, we've touched on the automatic sanity checker and the methodology briefly for writing STPs. It's also important to note that neither of these have any dependence on the proof or the status of an implementation. So this could be leveraged or written at any point in the development cycle, akin to test-driven development. But if we have a proof, we can further apply automation in the form of mutation testing. So we are able to automatically, given a passing proof, the original specification and the implementation, mutate the original specification in some way to derive some slightly different mutated spec. Now, we can then check to see if this mutated spec still allows the proof to pass. If the mutated spec lets the proof, like if the proof still passes given this mutated specification, that serves as a pretty specific hint to the developer that, hey, we found this different spec and our proof still passed. What's going on here? And so we can provide that as a specific hint to the developer of this difference between the original specification and what is not allowed by this new mutated specification. And this is a hint to focus the testing effort on trying to understand and ask this question of whether or not that's actually intended or not. We automatically generate these mutations, but as some of you may be guessing, not all mutations we generate are relevant to consider. In this same example, if we were to, let's say, come up with a mutated specification that's weaker than our original spec, we would expect the proof to pass, but we would also not be given any new information because all of the behaviors contained in the original spec are also contained in this weaker specification. So we can safely filter these out and remove the chance of potentially alerting the developer to any false positives. In general, we start with the original specification. We then create a number of mutations, mutated specifications based on mutation operators. We then are able to automatically filter that set of mutations based on some automatic tests, like the relative logical weakness, as well as testing to make certain that the mutations are not causing the proof to go through trivially. The set of remaining mutations we then test with the full end-to-end proof, and if the full proof passes, we consider that an alive mutation and a hint to the developer for further investigation. We further classify the set of alive mutations into a DAG based on relative logical strength, presenting the tester with only the root of each component of the DAG, which serves as the strongest hint to then minimize what is actually expected for them to investigate further, hopefully by writing STPs. So just to recap, the IronSpec prototype consists of 3 different testing techniques that all kind of help focus the testing procedures on trying to identify these divergences of intent, where the automatic sanity checker looks for these general kind of common cases where there's a clear disconnect between the specification and the input-output. STPs help answer context-specific questions based on the understanding of the actual tester, and mutation testing helps try to automatically find differences between the specification and the corresponding implementation. So as I mentioned before, we've built this in Dafny to be able to test Dafny specifications, and we've applied it to a corpus of in-house specifications, but we've also applied it to the specifications of 6 different open source verified systems, and we're able to find 10 different specification bugs across these 6, most of which have already been confirmed by the corresponding authors. As I mentioned before, STPs will always be the end of the story because they help answer that either proving a counterexample or proving that the behavior is correct, but we've also kept track of which aspect of IronSpec led to that initial hint, which then led to the discovery of these different specification bugs. Whether it be the hints from the automation, either the automatic sanity checker or the mutation testing, or just the 3 rows labeled STPs are the result of writing a suite of STPs like one would write a suite of unit tests. So the results help show that by applying these testing techniques that we use in imperative code to specifications, it's useful in actually increasing the reliability by identifying cases where the intent of the developer diverged from what was actually written. And with that, thank you for listening. I'm happy to take any questions if there are any.
In the examples, so the bugs you found in the specs, I mean, did those end up actually, were the specs just too weak, or did it also turn out that the implementations had bugs because of the too weak specs?
So there was a mix. I would say most of those cases, we found that the specification was too weak, but the actual system was correct.
Okay.
There were 2 cases where the system was too weak and that bug translated. But for the most case, it was just a under specification, either because they missed it, they didn't think it was necessarily important, but a different implementation could have contained some bad behavior. But yeah, there were a few, and then there was one example of finding a specification that was too strong. So there was an example of a specification for a QBFT protocol where the authors specified the adversary behavior, but it was too restrictive, we found. And by weakening it to be what we thought was a correct behavior for the adversary, we found that the proof actually broke. And then we went through the efforts of fixing the proof to see what was actually going on. But in terms of either case, I guess I would say that the examples that I talked about with the mutation testing looking for 2 weak specifications, it also works the other way. If, let's say I want to test the preconditions to make certain the preconditions of a method are not too strong, or in this case an adversary is overly restricted, you could still apply the mutation framework just with a different parameters.
Okay, if there are no other questions, let's thank Eli and